Okay, Assalamualaikum. Hi, everyone. So, today module 13, yeah, regarding HPPC emerging trends. Okay. So today, I will discuss about this topic. So we will explore about how next generation hardware frameworks, cloud architectures, AI, artificial intelligence are converging, yeah, to reshape the boundary of a modern high performance computing or HPC, okay, or HPPC, same thing. All right, okay. Okay, next. So here are the guidelines for today's lecture. So we will follow all this structure. So you can see that there is almost 10 points. Yeah. So our focus will cover heterogeneous computing, some introduction, heterogeneous AI integration, quantum-inspired system, energy-aware computing, and we will then evaluate the massive engineering feats behind X-scale deployment, edge computing convergence, cloud-based system, before we concluding with the new programming tool design to manage all this environment. Okay. So before we go further, yeah, on the topic, okay, regarding this, we need to look at the, yeah, 1 second. Okay, we need to look why, yeah, behind of this technology, high HPPC or high performance and parallel computing is evolving rapidly. So the driver behind this transformation is simple, yeah, because traditional architecture can no longer keep pace with the massive scaling demands of a modern data-intensive and computational-heavy applications. Same like our IP address, we cannot queue pipe anymore, so therefore we go to the IPv6, for example. Yeah. So because of that scenario, okay. So whether we are training a massive neural networks or processing a planetary scale Internet of Things data or underlying computing model must fundamentally change. Yeah. So that's why we have to improve all this because the traditional architecture can no longer support because of this scaling demand. Yeah. The technology, AI, and so on. Yeah. Okay. So this slide, actually, you can see that there is 8 main pillars or point of innovation we are tracking across the industry today. So this span from mixing multiple type of hardware chips within a single machine to moving entire supercomputing fabric into the cloud. Yeah. So let's examine each of these concepts sequentially to understand how they work and why they matters. Because this is very important because some activity maybe project I need you to explore, yeah, all this technology, especially in Microsoft Azure, Amazon, AWS, Amazon, I think, yeah, and then Google and any cloud platform. Okay, you can have a free. You have to try use that because that's the current demand right now. Yeah, about all this parallelism. Yeah. So our first major architecture trend shift away from the classic uniform processor model towards what we call heterogeneous computing. Okay, let's break down exactly what this means from a system level. Okay, here we are. Okay, by definition, a heterogeneous system combines completely different types of processor, such as for CPU or central processing unit, GPU, graphic processing unit, GPU, FPGA for field programmable gate arrays, and TPU stand for tensor processing unit, all working together within the same system fabric. So the structural significance of this approach is highly impactful. Instead of forcing a general purpose CPU to struggle with the massive vector maths, especially mathematical, we achieve immense performance and energy efficiency gains by offloading specific mathematical tasks to the most specialized, suitable piece of hardware available. To write software for this mixed environment, developers rely on advanced parallel computing or advanced parallel programming technologies, including from NVIDIA, CUDA framework, and GPU acceleration. And also OpenCL, so the open standard OpenCL framework and the Intel Unified cross-architecture development runtime, and also one API. So this one, the next one, okay? Next issue, AI and HPPC integration. So we move beyond the physical hardware to look at workload convergence. We are seeing an intense blending of artificial AI and machine learning workload directly into traditional supercomputing tasks. Okay, this integration goes both ways. We define this trend as the blending of machine learning algorithm directly into traditional physics-based HPPC simulation. The scientific significance here is revolutionary. By embedding AI model inside heavy computation, we can achieve intelligent approximation and optimization. This means a trained neural network can instantly approximate complex equation that used to take a supercomputer days to solve linearly, vastly accelerating scientific modeling and big data analytics. Excellent real-world example for this deep learning based weather forecasting model that predicts storm trajectories in real time, AI enhanced molecular modeling tool used for rapid drug discovery and material sciences. So that's kind of the example. Okay, there could be more, you can find it there. All right, okay. The next, quantum inspired and hybrid computing. So this is a third point, bridge. Third point, can say is to the silicon-based hardware and the future of computation. Okay, let's look at how quantum algorithms are being mapped onto classical supercomputer through quantum-inspired and hybrid computing. So, true fault-tolerant quantum hardware is still scaling up, but we don't have to wait to leverage its mathematical insight. This paradigm or concept focuses on incorporating quantum algorithm or quantum simulation techniques directly into classical HPPC workflow. So the engineering significant is that it offers potential exponential speed up for highly specific complex problem domain, most notably in combinatory optimization, for example, advanced logistic, cryptography. So the active industry trend right now is focused on designing hybrid classical quantum system, where a classical supercomputer, the overall application workload and route specific, highly complex mathematical formula out to a quantum coprocessor. So these are significant of the quantum inspired and hybrid computing. Next, energy aware. As our performance limits climb, our power requirements scale up drastically as well. This brings us to critical operational paradigm or concept energy aware computing. So energy aware computing. So in the modern landscape, raw performance is no longer our only target. We must also balance performance per watt. Energy aware computing focuses on designing hardware system, scheduling software, and underlying math algorithm to be intrinsically more energy efficient. Very important in balance in between right now. Okay, so we got a problem in that also. So this is absolutely critical for reducing massive power consumption and cooling costs in large-scale data and computing centers, which can draw megawatts of electricity. To manage this, we deploy advanced infrastructure technique like dynamic voltage and frequency scaling, or we call that DBFHAs. Yeah, DBFHAs. Dynamic voltage and frequency scaling, DBFS, which automatically throttle a processor clock speed up or down depending on the immediate workload, alongside energy efficient job scheduling software that bundle tasks to maximize power profile. So next, for the about the scale, exascale computing is about scale. So the ultimate benchmark of the raw computing capability is measured by generational milestone, and we have officially entered the era of exascale, or X-scale computing. For the X-scale computing, by defining an X-scale computing or system is a computing cluster capable of performing at least 10 power of 18 or 1 quintillion floating point operation per second, commonly abbreviated as a significing this scale cannot be overstated. It enables scientists to run ultra high resolution, highly accurate simulation across climate modeling, nuclear physics, and complex genomics that are mathematically impossible just a few years ago. Leading example of deploy exascale supercomputer include the Frontier system at Oak Ridge National Library. You can find that. Aurora at Argonne National Library, and also okay. can have a look about the Exascale supercomputer. Okay, now for Edge and HPC convergent. Yeah. While Exascale system centralized computing power, another major trend does the exact opposite by spreading computing out to where data is actually collected. Yeah. So let's look regarding Edge and HPC convergent. Okay, we define this concept as the tight integration of localized edge computing devices with centralized back-end high-performance computing centers to allow seamless real-time data processing. So the operational significance, is that it removes network latency and bandwidth bottleneck. This infrastructure design is absolutely essential for next generation safety critical application. For instance, autonomous vehicle must process sensor data locally on the edge to make split-second driving decision while simultaneously uploading telemetry back to an HPC core for large-scale fleet training and IoT analytics. So next, cloud-based HPC. So we address how organizations assess this massive computing power. Supercomputing is a shifting away, from the strictly on premise physical infrastructure toward cloud-based HPC, also known as HPC as a service. Okay, HPC as a service. So by definition, cloud HPC means provisioning full high performance computing capability through remote cloud perform on demand. So this concept delivers three massive business and engineering benefit on demand scale. Scalability meaning you can spin up 10,000 cores for a single hour, right? And then extreme cost efficiency because organization avoid the multi-million dollar capital expenses of building a physical server room and complete structural flexibility to adapt to shift project demands. Major cloud native provider leading this market space today, as I told you before, like AWS from Amazon, parallel cluster. You can use Microsoft Azure also, you can use that, try. And then Google Cloud HPC platform also. So this could be one of the thing that you need to explore in the later activity, especially I think, related to this one. There will be some tasks you need to explore about this. Because at the beginning time, it is totally free. You can access that, but I'm not sure right now. So, but anyway, try explore for that and then give some report regarding all these kind of the services on HPC. Okay, next, new program model and tools. So having explored the hardware, so the cloud and the location of these computing nodes, we must address the software side. How do developers actually write code for this complex environment? So that's what we did, right? So let's review a new programming models and tools. Okay, as architectures grow more complex, okay, the mixing CPU, GPU, and all the network clouds. The core purpose of new programming model is to drastically simplify software development on these diverse, multi-tier architectures, rather than writing entirely separate code bases for different hardware brands. Developers use modern unified technologies. So this include OpenMP 5.x, which is features advanced device F loading clauses, and then SYCL also, and Intel DPC++, which provides single source C++ development for heterogeneous system and perform portability, abstraction layer like FOCOS and also RAJA, so or Raja. So these tools, deliver three major benefit: complete code portability, peak hardware performance optimization, and immense ease of use across highly diverse hardware platform. Okay, so conclusion. So we have traveled across the entire modern landscape of the high performance parallel computing. Let's tie all of these thread together into our final conclusion. So to summarize our lecture, to summarize our lecture, the field of the HPPC or high performance and parallel computing is advancing at a breathtaking phase. By incorporating these emerging trends, the entire discipline is successfully redefining how complex computation are carried out. We are moving into an era of unprecedented computational efficiency, seamless like infrastructure scalability and intelligent integration that directly empower modern scientific, industrial, and also commercial breakthrough. Yeah. All right. So that's all. Bring us to the end of module 13. Thank you all very much for your time and for your attention. So that's all for today. Thank you. Bye bye.